In the summer of 2023, NASA nearly lost its oldest working spacecraft over a single faulty command. For 2 straight weeks, no one on Earth knew whether humanity's most distant working machine was still alive. Voyager 2, more than 12 billion miles from home, had gone completely silent. The fix NASA eventually attempted had never been tried at that distance before. It meant shouting into the void with the most powerful transmitter on the planet, hoping a 46-year-old spacecraft was still listening. That moment, and everything that has happened to Voyager 2 since, is a far stranger story than most people realize, and none of it needs any exaggeration to be genuinely remarkable. Here's what actually happened out there, what's happening to this spacecraft right now, and how much longer humanity's longest-running conversation with deep space actually has left. Voyager 2 launched in August 1977, technically a few weeks before its twin, Voyager 1, even though Voyager 1 took a faster, more direct route out of the solar system and eventually passed it. Voyager 2 took the scenic route instead. That choice made it the only spacecraft in history to fly past all 4 of the solar system's giant planets: Jupiter, Saturn, Uranus, and Neptune. That flight path only worked because of a rare planetary alignment that occurs roughly once every 175 years, allowing a single spacecraft to use each planet's gravity to slingshot toward the next, rather than relying entirely on its own limited fuel. Miss that launch window, and the mission, as it actually happened, simply wouldn't have been possible. Along the way, it delivered some of the most important planetary discoveries of the 20th century. Active volcanoes on Jupiter's moon, Io, geysers erupting on Neptune's moon, Triton, the bizarre sideways tilt of Uranus and its magnetic field, and close-up views of Uranus and Neptune that no other spacecraft has matched to this day, since nothing else has ever been sent to either planet since. Both Voyagers also carry something far more symbolic than any scientific instrument: a gold-plated record containing sounds, images, music, and greetings from Earth, sealed in a protective case engraved with instructions for how to play it, in case anything out there ever finds it. The team behind that record, led by astronomer Carl Sagan, spent months debating exactly what should represent humanity to any future finder, ultimately settling on a mix of natural sounds, greetings in dozens of languages, and a carefully chosen selection of music meant to say something true about life on Earth, without claiming to speak for all of it. By the time the mission's original planetary tour wrapped up in the late 1980s, both spacecraft kept going, eventually crossing the heliopause, the boundary where the sun's influence gives way to true interstellar space. Voyager 1 crossed that line in 2012. Voyager 2 followed in 2018, becoming only the second human-made object ever to leave the bubble our sun carves out of the galaxy. Both spacecraft are still out there right now, still transmitting, still technically part of an active NASA mission nearly 5 decades after launch, something absolutely nobody on the original engineering team expected, since the mission was designed to last only about 5 years. Every additional year of operation since then has effectively been bonus science nobody originally planned for, gathered by hardware, never built with anything like this kind of lifespan in mind. That brings us to July 2023, and the incident that came closer than almost anything before it to ending Voyager 2's mission for good. On July 21st, mission controllers at NASA's Jet Propulsion Laboratory sent a routine series of planned commands to the spacecraft. Something in that sequence went wrong, and instead of keeping its high-gain antenna locked precisely on Earth, the antenna tilted about 2 degrees off target. 2 degrees sounds tiny, almost trivial, the kind of error you wouldn't even notice pointing a flashlight across a room. But Voyager 2 was more than 12 billion miles away at the time, and at that distance, a 2-degree misalignment is enough to completely sever the connection. The spacecraft could no longer receive commands from Earth, and its signal became too faint and too poorly aimed for the Deep Space Network's antennas to make sense of it. Voyager 2 went completely silent. To put that distance in perspective, radio signals travel at the speed of light and still take roughly 18 to 19 hours to cross that gap in one direction, meaning any single exchange between mission control and the spacecraft, a command sent out and a response received back, eats up the better part of 2 full days before anyone on Earth even knows whether it worked. Under normal circumstances, this wouldn't have been an immediate crisis, because Voyager 2 has a built-in safety routine that automatically resets its orientation and repoints its antenna toward Earth several times a year, purely as a precaution against exactly this kind of drift. The problem was timing. That automatic reset wasn't scheduled to happen again until mid-October, nearly 3 months away, and nobody at NASA could be completely certain the spacecraft would survive that long without any way for engineers to intervene if something else went wrong in the meantime. For a spacecraft running on power sources that have been slowly decaying since the Ford administration, 3 months of complete silence was an uncomfortably long time to simply wait and hope, especially with no way to check in, no way to send a diagnostic command, and no way to know if some unrelated fault might strike while the antenna sat pointed uselessly into the dark. So the team tried something that had essentially never been attempted at that kind of distance before. Engineers at the Deep Space Network's giant radio dish in Canberra, Australia, prepared what they informally nicknamed an interstellar shout, a command sent using the single most powerful transmitter available anywhere in NASA's network, essentially maxing out the signal strength in hopes it would be strong enough to reach Voyager 2's antenna, even while that antenna was pointed slightly away from Earth, rather than perfectly aligned to receive it. Nobody on the team was confident it would actually work. Sending the command took over 18 hours to physically reach the spacecraft at the speed of light, and then, if it worked, it would take another roughly 18 hours for any response to make the return trip back to Earth. That meant a wait of well over a day and a half before anyone would know whether the gamble had paid off, or whether Voyager 2 was going to spend the next 3 months completely cut off, with no way of confirming it was even still functioning. In the meantime, the Deep Space Network kept listening for anything at all, and at one point managed to detect a faint carrier signal, essentially just a heartbeat confirming the spacecraft's transmitter was still powered on, even though the signal itself was far too weak to carry any actual data. That faint heartbeat was enough to keep hope alive, while the team prepared their one real shot at fixing the problem directly. On August 4th, 2023, the signal came back. Voyager 2 had received the shout, repointed its antenna, and resumed sending normal telemetry and science data, exactly as if nothing unusual had happened. NASA's own account of the moment described engineers watching data start flowing again after roughly 2 weeks of total silence, the longest gap in communication the mission had experienced in its entire history up to that point. It turned out to be one of the more dramatic real-world demonstrations of just how thin the margin for error has become on a spacecraft this old, operating this far from home, with no possibility of a repair crew, a reboot button, or any backup plan beyond extremely careful engineering and a healthy amount of hope. NASA's public celebration of the moment was almost understated, given how close things had actually come. A short statement confirming that full communication had been restored and that the spacecraft remained on its expected trajectory. Business as usual for a machine that had just survived one of the tensest stretches of its entire operational history. That close call also highlights something people tend to underestimate about Voyager 2, just how serious its long-term power situation actually is, and how deliberately NASA has been managing a slow-motion countdown for years now. Both Voyager spacecraft are powered by radioisotope thermoelectric generators, devices that produce electricity from the heat given off by the natural radioactive decay of plutonium-238. That decay process can't be paused, reversed, or refueled, which means each spacecraft steadily loses a small, predictable amount of electrical output every single year, roughly 4 watts less annually on each probe. There's no way to add power back, no solar panels that could help this far from the sun, and no possibility of ever sending a repair mission this deep into interstellar space. The only tool NASA's engineers actually have is deciding which systems to switch off, and in what order, to stretch the shrinking supply as far as it will possibly go, a task that has essentially become an ongoing exercise in triage rather than routine operations. Each Voyager originally carried 10 separate science instruments. Most have already been shut down over the decades, largely instruments specifically built to study the planets up close, which simply had nothing left to observe once the spacecraft moved on into open interstellar space. Instruments designed to photograph a planet's cloud tops or measure its rings serve no purpose, once there are no more planets left to visit. In more recent years, the shutdowns have become more painful, because the instruments still running are the ones actually gathering unique data about interstellar space itself, information that literally no other spacecraft anywhere has ever collected, since Voyager 1 and Voyager 2 remain the only 2 human-made objects to have traveled this far. In October 2024, NASA switched off Voyager 2's plasma science experiment. In March 2025, its low-energy charged particle instrument went dark as well, a shutdown that took roughly 23 hours just for the command to physically reach the spacecraft, a small but vivid reminder of exactly how far away this machine actually sits. According to NASA's own mission updates, its cosmic ray subsystem is scheduled to be switched off sometime in 2026, leaving the spacecraft down to just its magnetic field and plasma wave instruments for the foreseeable future. Voyager 1 has followed a nearly identical shutdown schedule on its own side, since both spacecraft carry essentially matching hardware and face the exact same power constraints, even though they're now positioned in different directions and at different distances from Earth after decades of independent travel, with Voyager 1 currently holding the distinction of being the single most distant human-made object in existence, having taken the more direct route out of the solar system from the very beginning. Engineers have even found creative ways to squeeze out a little extra runway, including tapping into a small reserve of backup power, originally set aside purely as a safety buffer for the spacecraft's voltage regulation system, a mechanism designed to protect the remaining instruments in case of a sudden, potentially damaging voltage swing. Rather than continuing to hold that reserve untouched indefinitely, the mission team made a deliberate decision a few years back to start actively spending that safety margin now in exchange for a few more years of active science later, essentially betting that the benefit of continued operation outweighs the small added risk of running without that particular backstop. It's the kind of trade-off that only makes sense on a mission this far along, where every additional instrument kept alive for even one more year represents genuinely irreplaceable data that nothing else in existence is currently positioned to collect. If everything continues roughly according to plan, NASA's current projection is that both Voyager spacecraft should be able to keep at least one working science instrument running into the early 2030s, more than half a century after launch, before power finally drops too low to keep anything meaningful operating at all. As of the most recent mission updates in 2026, both spacecraft are still alive, still transmitting, and still remarkably doing real science from a region of space no other human-built object has ever reached, sending signals that now take more than a full day to arrive back on Earth, given the distance involved. Even after every science instrument eventually goes silent, engineers expect the spacecraft could technically continue transmitting basic engineering telemetry for a little while longer. A faint signal confirming the machine is still alive and, in some limited sense, still there, right up until the power finally drops below the threshold needed to run anything at all. There's something genuinely worth sitting with in just how fragile all of this actually is, without needing to invent anything extra to make the story feel significant. This is a machine built with 1970s technology, using computers with a small fraction of the processing power of a modern calculator, running on a power source that has been quietly fading since before most of the people currently operating it were even born, sitting farther from Earth than any other human-made object in history, completely beyond any possibility of physical repair. A 2-degree antenna error, something you could accidentally cause by bumping a tripod, nearly ended 50 years of continuous operation in a matter of weeks. And yet, it didn't end. Engineers found a way to shout across 12 billion miles of empty space and got an answer back. Think about what that actually required. Holding institutional knowledge about a spacecraft's exact hardware quirks across nearly 5 decades, keeping ground station equipment from the 1970s still compatible with modern control systems, and trusting that a command sent at the absolute limit of available transmitter power would somehow reach a target moving farther away with every passing second. Voyager 2 isn't sending back some mysterious new signal humanity can't explain, and nothing about its recent behavior suggests any kind of external interference or unexplained intelligence responding to it out there. What it is doing, when you actually look closely at the real engineering involved, is arguably just as remarkable. It's still working. It has been continuously operating for nearly 50 years, using power that decays a little more every single year with no way to ever replace it, carrying humanity's actual greeting to the rest of the universe on a golden record bolted to its side. And it's still, right now, sending back real information about a region of space we've never explored with anything else. NASA's own engineers have openly said that every single day these spacecraft manage to keep operating is essentially a bonus nobody fully expected to get, and that any given transmission could, in principle, turn out to be one of the last. That's not a manufactured mystery. That's simply the honest, ongoing reality of trying to keep a 50-year-old machine alive at the very edge of what our species has ever managed to reach. And it's a story that doesn't need a single invented detail to be worth paying attention to. The mission itself is entering genuinely uncharted territory in a very literal sense, not just scientifically, but organizationally. Ed Stone, who served as the Voyager program's chief scientist for decades and oversaw the mission through every major planetary flyby from Jupiter all the way out to Neptune, stepped back from that role a few years ago after devoting more than half his life to this single project, a length of institutional memory that's genuinely difficult to replace on a mission where the people who originally built the hardware retired long ago, and where the original engineering drawings sometimes exist only on paper in archives rather than in any searchable digital format. Suzanne Dodd, the current Voyager project manager at JPL, has been candid in public statements about just how deliberately the team is now rationing what remains, describing the ongoing instrument shutdowns as the price of keeping the spacecraft alive as long as possible rather than accepting an earlier, more abrupt end to the mission. Every decision about which system to switch off next carries real weight, because once an instrument goes dark, there's no scenario in which it ever comes back on again. Every choice the team makes now is effectively permanent, decided years or even decades before the actual power runs out completely. There's also something quietly poetic about what happens after the instruments finally do go silent for good. Even once every last piece of active science equipment has been switched off and Voyager 2 can no longer send back any usable data at all, the spacecraft itself doesn't simply vanish or stop existing. It keeps moving, having already left the sun's protective bubble behind years ago. It will simply continue drifting outward through the emptiness of interstellar space indefinitely, carrying that golden record along with it for what could effectively be an unimaginably long stretch of cosmic time. Since there's essentially nothing out there to slow it down, damage it, or wear it away the way weather and erosion would on Earth, scientists have estimated that the record itself, engineered specifically to survive the harsh conditions of deep space, could plausibly remain readable for hundreds of millions of years, long after the sun itself will have changed, and long after anything resembling human civilization as it exists today could possibly still be around to remember having sent it. It's worth pausing on exactly what Voyager 2 has actually been teaching scientists since it crossed into interstellar space, because the region itself turned out to be stranger than anyone fully expected before either spacecraft got there. Researchers had assumed the boundary between the heliosphere and true interstellar space would be a relatively gradual transition, with plasma density and magnetic field strength shifting slowly over some distance. Instead, both Voyagers detected a surprisingly sharp edge, more like crossing a real boundary than drifting through a gradual fade, with plasma density jumping abruptly once each spacecraft actually crossed over. Voyager 2 also carried a working plasma instrument at the exact moment it made that crossing. In 2018, something Voyager 1 didn't have available when it crossed 6 years earlier, giving scientists a much more detailed picture of what that transition actually looks like in real time, rather than having to reconstruct it after the fact from indirect measurements. That single difference between the two spacecraft, one still having a functioning plasma instrument at exactly the right moment and one not, turned out to matter enormously for how much we now understand about where our solar system actually ends and the wider galaxy genuinely begins. Beyond the heliopause crossing itself, Voyager 2's instruments have continued sending back genuinely puzzling readings about interstellar space that researchers are still working through. Magnetic field measurements from out there have shown patterns that don't perfectly match what earlier theoretical models predicted, hinting that the true structure of the local interstellar medium, the thin cloud of gas and dust the sun is currently passing through, is more complicated and less uniform than scientists assumed before actually having a spacecraft physically sitting inside it to check. None of that ambiguity requires any exotic explanation. It simply reflects the plain fact that nobody had ever collected real, direct measurements from this exact region of space before, and reality has a habit of turning out more complicated than any model built entirely from a comfortable distance back on Earth. What makes this story worth telling right now in 2026 is that we're likely watching the final stretch of an achievement that will probably never be repeated in quite the same way. Future spacecraft will eventually travel farther, carry better instruments, and send back sharper data, but they won't be Voyager 2. They won't carry the specific golden record assembled by a team led by Carl Sagan in the 1970s. They won't have flown past all 4 giant planets on a single trajectory that will likely never be repeated, given how rarely the outer planets align the way they did during that launch window. And they won't have already spent close to half a century quietly proving that a machine built before most of its current operators were born can still teach us something new about the universe. Every single day, it manages to stay switched on. Every engineer currently working on the Voyager team knows they're managing the tail end of something that began before they were hired, and in many cases, before they were even born, inheriting decades of careful, painstaking decisions made by people who could never have known exactly how long their work would ultimately need to last. Somewhere out past the edge of the solar system right now, moving through space at roughly 10 miles every second, completely alone, running on a power supply with a hard and permanent expiration date, Voyager 2 is still listening for our commands and still calling back. However many years it has left, that alone remains one of the most quietly extraordinary things humanity has ever built.